The universe is a vast ocean of unanswered questions. We stand on the shore of cosmic knowledge, gazing at a horizon filled with profound enigmas that challenge everything we think we know. This journey will take us through 25 of the most compelling mysteries, from the invisible glue holding galaxies together to the ultimate fate of all reality. You will gain a front-row seat to the greatest unsolved puzzles of existence, the very frontiers where science meets the unknown. We will explore why we seem to be alone in a galaxy teeming with potential, and what happens to information that falls into a black hole. Which cosmic mystery do you believe holds the key to our future? Our universe is held together by a ghost. We see its handiwork everywhere, in the way galaxies spin far too quickly to stay intact, in the way light bends around massive clusters of galaxies. Yet this cosmic architect, this invisible scaffold, refuses to show itself. We call this ghost dark matter. It is the universe's most influential missing person. We are certain it exists because we can watch its gravitational pull at work. Stars at the outer edges of spiral galaxies should be moving slower than those near the bright center, just as Pluto orbits our Sun more slowly than Earth. But observations show they race around at nearly the same speed. The only explanation is that the entire galaxy is embedded within a vast, heavy halo of something we cannot see, a gravitational glue preventing the galaxy from flying apart. This unseen mass also acts as a cosmic lens, warping the path of light from distant objects in a phenomenon called gravitational lensing. The sheer amount of bending we observe tells us there is far more matter present than the glowing stars and gas we can detect. So what is it made of? The hunt for an answer has led physicists to propose some truly exotic candidates. One leading idea is WIMP, or weakly interacting massive particles. These are theoretical heavy particles that barely interact with normal matter, passing through our planet, our homes, and even our bodies as if we were not even there. Another candidate is the Action, an incredibly light particle that could be flowing through the cosmos in vast numbers. There are even more speculative ideas, like the possibility that dark matter is made of primordial black holes formed in the universe's first moments. After decades of searching with incredibly sensitive detectors buried deep underground, we have yet to directly catch a single particle of dark matter. It constitutes about 27% of the entire cosmos, nearly 6 times the amount of ordinary matter that makes up you, me, and every star we can see. It is the dominant architectural force of the universe, and we have no idea what it is. How can something so fundamental to the structure of everything remain so perfectly hidden from our finest instruments? This is not just a gap in our knowledge, it is a chasm, forcing us to question whether we even understand the basic ingredients of reality. If dark matter is the invisible architect, then dark energy is the universe's ghost in the machine, a force of pure, repulsive gravity. Its discovery at the close of the 20th century was a profound shock. Astronomers were observing distant stellar explosions, supernova, to measure how much the universe's expansion was slowing down over time. The prevailing belief was that the gravitational pull of all the matter in the cosmos would eventually put the brakes on the Big Bang's initial momentum. Instead, they found the opposite. The most distant supernova were fainter than expected, meaning they were farther away than they should have been. The expansion of the universe was not slowing down at all. It was speeding up. Some unknown repulsive force, now called dark energy, was pushing galaxies apart at an ever-increasing rate. This was not just a new discovery, it was a complete overturning of our cosmic expectations. What could possibly be causing this? The leading candidate is the cosmological constant, an energy inherent to the vacuum of space itself. Think of empty space not as truly empty, but as a seething foam of virtual particles popping in and out of existence. This quantum activity could generate a constant, gentle pressure that stretches the very fabric of the cosmos. If this idea is correct, then dark energy's strength remains unchanging over time, a permanent feature of reality. But there is another, more unsettling possibility. What if dark energy is not constant? What if it is a dynamic field, similar to the one that drove the universe's explosive birth during inflation, but far weaker? This field could evolve, its strength increasing or decreasing as the cosmos ages. This leads us to one of the most dramatic potential futures for our universe, a scenario known as the Big Rip. If the repulsive force of dark energy grows stronger over billions of years, it would eventually overcome every force that holds things together. First, the acceleration would shred galaxy clusters, sending galaxies flying off into the eternal darkness. Then it would tear apart individual galaxies. Later, as the force intensifies, it would rip stars from their planetary systems. In the final, terrifying moments, the escalating expansion would overcome the forces holding atoms together, and then even the nuclear forces within atomic nuclei. The very fabric of space-time would be torn asunder, ending the universe not with a cold, slow fade, but with a violent, fundamental dissolution of reality itself. The true nature of dark energy, this mysterious 70% of the cosmos, will ultimately decide whether our universe faces a quiet, cold end or a violent, explosive one. It is the force writing the final chapter of our cosmic story, and we have only just begun to read the first few words. Yet for all the universe's unseen forces and dark energies, there is another, more personal void that confronts us. We gaze at a sky filled with hundreds of billions of galaxies, each home to hundreds of billions of stars, with countless planets likely orbiting in habitable zones. The numbers alone scream that we should not be alone. So where is everybody? This is the core of the Fermi Paradox, the stark contradiction between the high probability of extraterrestrial life and our total lack of any evidence for it. The silence is deafening. One deeply unsettling answer is the Great Filter hypothesis. This idea suggests that at some point between the emergence of non-living matter and the creation of a galaxy-spanning civilization, there exists a barrier, a step so difficult that almost every potential civilization fails to cross it. The terrifying question is, where does this filter lie in our own past? If it is behind us, perhaps the leap from simple single-celled life to complex multicellular organisms was a cosmic fluke of unbelievable rarity. That would mean the galaxy is largely silent, filled with microbial life but devoid of other thinkers. But if the Great Filter is still ahead of us, then the silence is a warning. It could mean that every advanced civilization eventually discovers a technology, perhaps in physics or biology, that inevitably leads to its own destruction. Our own technological adolescence would then be the calm before a storm that no one survives. Other possibilities are less ominous but equally strange. Perhaps intelligent life is common, but it evolves in forms so alien that communication is impossible. Their thoughts, their technology, their very perception of reality might be as incomprehensible to us as a symphony is to a rock. Or maybe the cosmos is simply too vast, and the timescales for civilizations overlapping are too short. We might be like ships passing in an unimaginably enormous ocean, blinking in and out of existence in a cosmic instant without ever noticing one another. There is also the zoo hypothesis, the idea that advanced civilizations are aware of us but have chosen to observe from a distance, following a form of galactic non-interference until we reach a certain level of maturity. Or perhaps they have transcended physical reality altogether, migrating into vast simulated worlds or dimensions beyond our perception, leaving the quiet, material universe behind as a forgotten relic. Each potential solution to the great silence forces us to look inward, to question our own future and our place in the cosmos. Are we the universe's first and only children, its lonely inheritors, or are we simply too young or too naive to hear the conversation that is already happening all around us? The profound silence of the cosmos is unsettling, but the nature of reality itself faces an even deeper crisis at the edge of a black hole. Here, two pillars of modern physics, Einstein's general relativity and quantum mechanics, wage a silent war with consequences for the very fabric of the universe. The battleground is the black hole information paradox. According to Einstein's theory, a black hole's boundary, its event horizon, is a point of no return. Anything that crosses it is lost forever, crushed into a single point of infinite density called a singularity. The identity of what fell in, whether it was a star, a cloud of dust, or a library of books, is seemingly erased from our universe. This aligns with classical physics, which has no problem with information being permanently lost. But quantum mechanics, the rules governing the very small, has a fundamental, unbreakable law. Information cannot be destroyed. It can be scrambled, transformed, or hidden, but it must, in principle, be recoverable. For decades, physicists assumed this conflict was purely theoretical, that information was simply trapped inside the black hole, out of reach but still technically existing. Then Stephen Hawking made a startling discovery. He realized that due to quantum effects near the event horizon, black holes are not completely black. They slowly emit a faint glow of radiation. This Hawking radiation is incredibly subtle, but it carries energy away from the black hole, causing it to lose mass over unimaginable eons until it completely evaporates, vanishing from existence. And here lies the paradox. The Hawking radiation that escapes appears to be completely random, purely thermal noise that carries no information about what fell into the black hole. So when the black hole finally evaporates, all the information about everything it ever consumed is gone. Poof, vanished. This violates the core principle of quantum mechanics. We are left with a universe that has lost a fundamental ledger of its history. How can physics allow this? Resolving this paradox has forced scientists to propose some truly mind-bending solutions. One leading idea is the holographic principle. This suggests that all the information about what fell into the three-dimensional black hole is not lost inside, but is instead encoded on a two-dimensional surface like a hologram at its event horizon. The three-dimensional interior we imagine is just a projection of that data. When the black hole evaporates, the information is slowly and chaotically released back into the universe through the Hawking radiation, scrambled beyond easy recognition but not destroyed. Another, more violent solution is the firewall hypothesis. It proposes that the event horizon is not a smooth, empty space as relativity suggests, but a blazing wall of high-energy particles. Anything hitting this firewall would be instantly incinerated. This would preserve information by preventing anything from actually falling into the black hole in the first place, but it blatantly violates Einstein's principle that someone crossing the event horizon should feel nothing unusual. Both of these ideas rewrite our understanding of space and time at the most fundamental level. The information paradox is not just an academic puzzle. It is a direct challenge, a sign that our understanding of gravity and the quantum world is profoundly incomplete. To solve it, we may need a theory of everything, a framework that can finally unite the very large with the very small and tell us what truly happens when reality is stretched to its absolute limits. Sometimes the greatest mysteries are not found in the distant cosmos, but in the subtle, unexpected behavior of our own robotic explorers. As the Pioneer 10 and Pioneer 11 spacecraft journeyed beyond the orbits of the outer planets, scientists tracking their trajectories noticed something deeply puzzling. The probes were slowing down slightly more than the laws of gravity predicted. This tiny, persistent deceleration became known as the Pioneer Anomaly. For years, it was a ghost in the machine of our solar system, a faint but undeniable tug that seemed to defy our understanding of physics. The discrepancy was minuscule, equivalent to a 10 billionth of the gravity we feel on Earth, but over the vast distances of space it added up. Was it evidence of some unknown matter in the outer solar system? Could it be a sign that Einstein's theory of gravity needed a slight modification at these immense scales? The possibility of new physics hung in the air, a tantalizing whisper of a fundamental discovery waiting to be made. The answer, however, proved to be far more ordinary, yet no less brilliant in its revelation. Decades after the anomaly was first spotted, a dedicated team of researchers embarked on a monumental digital archaeology project. They recovered old data tapes, tracked down original blueprints, and built sophisticated thermal models of the spacecraft. Their conclusion was startlingly simple. The Pioneer probes were powered by radioactive generators, and the heat they emitted was radiating away from the craft unevenly. A little more heat was being emitted from the back of the spacecraft's main dish antenna than from the front. This created a tiny, constant photon thrust, a gentle push of light itself that acted as a brake, producing the exact amount of deceleration that had so mystified scientists. It was not dark matter or modified gravity. It was the subtle, unforeseen effect of their own warmth. The Pioneer anomaly stands as a powerful lesson in cosmic humility. It reminds us that the universe's secrets can be hidden in the most mundane of details, and that the patient, meticulous work of science is often its own greatest reward. The ghost was not in the cosmos, but in the engineering. A single, powerful burst of cosmic sound emerged from the silence. On August 15, 1977, a radio telescope at Ohio State University known as the Big Ear recorded something extraordinary. A volunteer astronomer, Jerry Amon, was reviewing the computer printout days later when his eyes fell upon a string of data so shocking he circled it in red pen and wrote one word beside it: wow. For 72 glorious seconds, a narrowband radio signal, precisely at the frequency of hydrogen, the most common element in the universe, blared from the direction of the constellation Sagittarius. It was exactly the kind of signal scientists had predicted an intelligent civilization might use to announce its presence, a focused beacon cutting through the cosmic noise. The signal grew in intensity as the telescope's beam swept across the sky, peaked, and then faded away exactly as expected, a perfect curve. It was not random, static, or a known human transmission. It was, for one brief moment, the candidate everyone had been waiting for. The search for an explanation began immediately, and the silence that followed was as profound as the signal itself. Despite decades of repeated listening, the wow signal never returned. It was a cosmic one-hit wonder, a scream in the dark that was never repeated. The mystery of its origin has only deepened with time. Could it have been a military transmission from a secret satellite, an undiscovered natural cosmic phenomenon? In 2016, a controversial theory emerged suggesting it was the reflected radio signal from a passing comet. But that idea has been largely debunked, as comets are surrounded by vast clouds of hydrogen gas that would produce a broad, messy signal, not the sharp, focused one that was detected. The signal's fleeting nature is perhaps its most defining and frustrating characteristic. If it was a deliberate beacon, why was it switched on for just over a minute? Was it a sweeping lighthouse beam from a distant star that only briefly illuminated Earth? Or was it a message meant for someone else and we just happened to be in the way? The wow signal remains the most tantalizing, unexplained event in the history of the search for extraterrestrial intelligence. It is a ghost in the cosmic radio spectrum, a single data point that proves we are listening but offers no answers, only a deeper, more haunting question. What if we heard a whisper just once and will spend the rest of eternity wondering what it meant? Even our most pristine map of the infant universe holds a ghostly imprint that seems to stare back at us. This map is the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was just 380,000 years old. According to our most fundamental cosmological principle, this radiation should be essentially the same in all directions, a nearly uniform sea of tiny temperature fluctuations that are random and isotropic. The universe on its largest scales should have no preferred direction, no center, and no edge. Yet, when scientists created exquisitely detailed maps from satellite data, they found something deeply unsettling. There appears to be a strange alignment, a preferred axis running through space that some have dramatically nicknamed the axis of evil. Along this axis, the temperature fluctuations in the cosmic microwave background show a peculiar coherence, a strange kind of order where our standard models predict there should only be chaos. It is as if the universe's very first fingerprint has a distinct, unexpected swirl. One of the most prominent features is a large cold spot, an area significantly cooler than its surroundings that aligns with this mysterious axis. This is not just a minor statistical fluke. The alignment seems to correlate bizarrely with the plane of our own solar system. This is the part that truly unnerves cosmologists. It suggests that what we are seeing might not be a feature of the early universe at all, but some kind of local contamination or foreground effect that we have not yet accounted for. Perhaps dust within our own galaxy is creating a pattern that we are misinterpreting as a cosmic signal. But if it is real, if this axis is a true feature of the primordial universe, then the implications are profound. It would mean the universe is not the same in all directions. It would challenge the Copernican principle itself, the foundational idea that we do not occupy a special place in the cosmos. We would have to consider the possibility that the Big Bang was not the true beginning, but was instead preceded by something else that left a scar, a pre-existing structure that imprinted its direction onto our newborn cosmos. Or perhaps our understanding of gravity itself is incomplete on the largest possible scales. Is the axis of evil a monumental clue, a crack in the foundation of modern cosmology pointing toward a deeper reality? Or is it simply the most compelling cosmic mirage we have ever encountered, a trick of statistics and perspective that will fade away with better data? For now, it remains a silent, unsettling challenge to our picture of a perfectly random and isotropic universe. Far beyond the orbit of Neptune lies a frozen frontier, a vast disk of icy worlds known as the Kuiper Belt. This is the solar system's attic, filled with ancient relics from the era of planetary formation. For decades, we expected this reservoir of comets and dwarf planets to extend smoothly for billions of miles, its population gradually thinning out into the darkness. But our observations have revealed something far stranger. There is a cliff, at a distance of about 50 astronomical units, roughly where Pluto orbits. The number of Kuiper Belt objects is abundant. Just a little farther out, beyond this invisible boundary, the population of these icy bodies plummets. It is not a gentle decline, but a dramatic and abrupt edge, as if the builders of the solar system simply stopped their work. This Kuiper cliff presents a puzzle with profound implications. Why does our solar system appear to have a hard stop? One of the most compelling theories points to the gravitational hand of an unseen giant. Astronomers studying the orbits of the most distant known objects have noticed that several of them cluster in a way that suggests they are being herded by the persistent tug of something massive. This hypothetical world, often called Planet 9, would be up to 10 times the mass of Earth and orbiting hundreds of times farther from the Sun than we are. Its immense gravity over billions of years could have sculpted the outer edge of the Kuiper Belt, clearing out a vast region and shepherding the remaining objects into peculiar, aligned orbits. The hunt for this phantom planet is ongoing, a modern-day celestial detective story. Yet there is another, even more dramatic possibility. What if the Kuiper Cliff is not the work of a hidden planet, but a fossilized scar from the solar system's violent infancy? In its first few million years, our Sun was born in a dense stellar nursery, surrounded by thousands of other newborn stars. It is possible that a sibling star passed dangerously close to our young planetary system. The gravitational tides from such a close encounter would have been catastrophic, violently stripping away the outer layers of the primordial Kuiper Belt and flinging countless icy worlds into interstellar space. This stellar flyby would have left behind a sharply truncated disk, a permanent monument to a traumatic childhood event. Is the edge of our solar system a billboard for a lost sibling star or the hunting ground of a dark giant? The answer lies in the silent, frozen dark, waiting for a telescope to finally pierce the veil and read the story written in ice. But what if we could send a message that arrives before it is sent? This is not mere science fiction, but a logical consequence of a hypothetical particle known as the tachyon. A tachyon is a theoretical entity that, by its very nature, must always travel faster than the speed of light. Unlike everything else in the known universe, it is thought to gain energy as it slows down, and it would require infinite energy to slow it to the speed of light itself. It is a particle forever locked in a superluminal state. The strangeness of tachyons is not just their speed, but what that speed implies for the fabric of causality, the unbreakable rule that cause must always precede effect. This leads us to the thought experiment of the tachyonic antitelephone. Imagine you have a device that can send messages using these particles. You send a message to a colleague on a distant planet, a planet orbiting a star 4 light-years away. Because your message travels faster than light, your colleague receives it almost instantly. Let us say just a few minutes later, they immediately send a tachyonic reply. And because their reply also travels faster than light, you receive it before you even sent your original message. You have just received an answer to a question you have not yet asked. This is a direct violation of cause and effect. It opens the door to the infamous grandfather paradox. What if the message you receive from the future instructs you not to build the antitelephone in the first place? If you obey the message, you would never build the machine, which means you could never receive the message telling you not to build it. This creates an unresolvable logical loop, a contradiction that shreds the timeline. The universe, as far as we understand it, does not permit such paradoxes. The fact that we do not observe these causality violations is a powerful argument that tachyons, if they exist at all, cannot be used to transmit information. They might be mathematical curiosities, ghosts in the equations of physics that can never manifest in a way that breaks the chronological order of events. The tachyonic antitelephone is more than a puzzle about faster-than-light travel. It is a fundamental test of our understanding of time itself, a stark reminder that the speed of light may be less about velocity and more about the very architecture of a consistent and paradox-free reality. Our reality seems solid and predictable, yet this is only a comforting illusion. Venture into the subatomic realm, and the very nature of existence becomes a cloud of shimmering possibilities. An electron is not a tiny, solid ball orbiting a nucleus. Until we measure it, it exists in a ghostly state of superposition, occupying not one location but a blur of all possible locations simultaneously. It spins in all directions at once. This is the heart of the quantum measurement problem, a mystery that forces us to question what it means to be real. The most established explanation is the Copenhagen interpretation. It proposes that this cloud of possibilities is not just a lack of knowledge, but the true state of the system. The electron really is everywhere it can be. Then, the moment we observe it, the moment a measurement is made, this probability wave collapses. The infinite possibilities condense into a single, definite outcome. The ghost becomes a particle. This raises a profound and unsettling question. What counts as an observation? Is it the eye of a scientist, the photographic plate of a detector, or does consciousness itself play a fundamental role in shaping reality? The idea that the universe requires an observer to snap it into focus is both mesmerizing and deeply strange, suggesting that the cosmos might remain in a hazy, unrealized state until a mind looks upon it. In stark opposition to this stands the many worlds interpretation. It offers a breathtakingly bold solution. There is no collapse. Every time a quantum system faces a choice, every possible outcome actually happens. The universe splits. In one branch, you measure the electron to be spinning up. In another, an identical version of you measures it to be spinning down. Both versions are equally real, both futures unfolding in their own separate, non-communicating timelines. This means that for every quantum event, reality is constantly branching into a vast, ever-growing multiverse of parallel existences. In one world, a stray quantum fluctuation allowed a distant asteroid to miss Earth. In another, it did not. The many worlds interpretation removes the special role of the observer, but at the cost of populating reality with an infinite number of slightly different versions of ourselves, forever unaware of one another. So which is it? Does our gaze force the universe to make up its mind, or are we merely one thread in an unimaginably vast tapestry of simultaneous realities? The quantum measurement problem is not an abstract philosophical debate. It is a fundamental gap in our understanding of how the world works, a crack in the foundation of physics that remains, for now, wide open. Our existence hinges on a single, unaccounted-for surplus. The universe we know, with its galaxies, stars, and planets, is built entirely from matter. But the Big Bang should have created a perfect mirror image of our reality. For every particle of matter born in that primordial fire, an equal and opposite particle of antimatter should have been created. Antimatter is the perfect twin of matter, identical in almost every way but with an opposite electrical charge. When a particle meets its antimatter counterpart, they annihilate each other in a flash of pure energy, leaving nothing behind. According to this perfect symmetry, the early universe should have been a vast furnace of matter and antimatter constantly colliding and mutually destroying one another. The entire cosmic drama should have ended almost as soon as it began, resulting in a universe containing nothing but a thin, uniform bath of radiation. There would be no atoms, no chemistry, no planets, and certainly no one to ponder this mystery. Yet here we are. For every billion annihilations in the first second of time, a single particle of matter somehow survived. That 1 in a billion imbalance is all there is. Every star, every galaxy, everything we see is made from that tiny, leftover residue. This is the baryon asymmetry problem, and it is the ultimate question of why there is something instead of nothing. Physicists believe the answer lies in a fundamental breaking of symmetry, a set of conditions known as the Sakharov conditions. One of the most crucial is a phenomenon called CP violation. CP stands for charge and parity. It means that the laws of physics should treat particles and their antiparticle mirror images identically, but we have found that they do not. In certain rare particle decays, matter behaves slightly differently than antimatter. It is a tiny, subtle preference, like a coin that lands on heads just a few more times than tails in a million tosses. The problem is that the amount of CP violation we have observed in laboratory experiments is far too small to account for the vast surplus of matter we see in the cosmos. It is like finding a single dropped coin and trying to explain the existence of all the world's treasuries. So the search is on for new, more powerful sources of this symmetry breaking. Experiments like the Large Hadron Collider are smashing particles together at incredible energies, trying to recreate the conditions of the early universe and catch a glimpse of new particles or forces that treat matter and antimatter more differently. Other projects are studying the properties of neutrinos, ghostly particles that barely interact with anything, to see if they could be their own antiparticles and hold the key to this cosmic imbalance. What process in the first fleeting moments of creation gave matter this decisive, 1 in a billion advantage? Without it, our universe would be a silent, empty void. We are the evidence of a broken symmetry, the children of a cosmic accident that should never have happened. This cosmic accounting error threatens to rewrite the textbooks. We call it the Hubble tension, and it is a direct conflict over the single most important number in cosmology, the Hubble constant. This number describes how fast the universe is expanding today. For decades, we assumed we could pin it down with ever greater precision, but the opposite has happened. Our two most trusted methods for measuring this expansion rate are now giving us answers that stubbornly refuse to agree. It is as if you used two different rulers to measure the same table and got two different definitive lengths. One method looks back to the dawn of time, to the cosmic microwave background. This fossilized light from the infant universe allows us to calculate how fast the universe should be expanding today based on our standard model of cosmology. The other method uses what astronomers call the cosmic distance ladder. They observe pulsating stars and cataclysmic supernova in our galactic neighborhood, carefully measuring their distances and speeds to get a direct local measurement of the current expansion rate. The results should align perfectly. They do not. The universe appears to be expanding significantly faster today, based on the nearby measurements, than the pristine early universe data says it should be. The discrepancy is not large, only a few percent, but the precision of our instruments has become so great that this small gap is now a yawning chasm. The chance that this is a simple error is vanishingly small. So what is causing the tension? One possibility is that we are missing something in our observations. Perhaps there is an unknown type of interstellar dust affecting the measurements of nearby supernova. Or maybe our understanding of the stars we use as standard candles is flawed. But as the data piles up, these simple explanations are becoming less and less likely. The far more exciting possibility is that this is a crack in our fundamental model of the universe. Our standard model includes dark matter and a constant form of dark energy. What if dark energy is not constant? What if its strength has been increasing over the life of the cosmos, causing the expansion to accelerate more quickly than our models predicted? This would explain why the universe is expanding faster now than the early universe data suggests. Alternatively, we might need a new type of particle, a previously unknown form of radiation that flooded the early universe and altered its expansion history just enough to throw off our predictions. Or perhaps dark matter possesses some strange, interactive properties we have not yet accounted for. The Hubble tension is more than a statistical anomaly. It is a direct challenge, a clue that our map of the cosmos, for all its sophistication, is missing a fundamental feature. Resolving it could force us to rewrite the story of dark energy or introduce entirely new ingredients into the cosmic recipe. The universe is giving us two different answers to the same simple question, and one of them must be wrong. Or perhaps, just perhaps, we are the ones who have been asking the question in the wrong way all along. A strange guest from the depths of interstellar space briefly entered our solar system, and its visit left more questions than answers. In October 2017, astronomers in Hawaii spotted a point of light moving at incredible speed. They named it Oumuamua, Hawaiian for scout. It was the first object ever detected that came from beyond our sun's influence. As telescopes around the world swiveled to track it, they revealed a visitor unlike anything in our own cosmic backyard. Its path was not a closed orbit around the sun, but a hyperbolic arc, a one-way ticket from one star system to another. But its trajectory was only the beginning of the mystery. The most startling feature was its shape. As it tumbled through space, the way its brightness changed revealed an object that was dramatically elongated, perhaps 10 times longer than it was wide. This was no typical roundish asteroid or comet. It was a cosmic cigar, a shape rarely seen in nature. Then came the real puzzle, its motion. As Oumuamua sped away from the sun, something was giving it an extra push. Its acceleration could not be explained by gravity alone. This non-gravitational acceleration is exactly what we see with comets when sunlight vaporizes their icy surfaces, creating jets of gas that act like a natural rocket engine. The crucial difference was that Oumuamua showed no visible signs of this activity. No surrounding cloud of gas and dust, no cometary tail. It was accelerating in total silence. So what was pushing it? One natural explanation proposes that Oumuamua was a new kind of object, a hydrogen iceberg. In the coldest depths of interstellar space, a chunk of solid hydrogen could form. As it neared the Sun, the warming would cause the frozen hydrogen to sublimate directly into gas, providing the thrust we observed without producing a visible tail, since hydrogen is invisible to our telescopes. Yet this idea has its own difficulties, as it is unclear whether such a fragile iceberg could survive a long journey through interstellar space. The strangeness of its properties led Harvard astronomer Avi Loeb to propose a more provocative hypothesis. What if Oumuamua was not a natural object at all, but a piece of advanced alien technology? He suggested its unusual shape and acceleration could be explained if it was a light sail, a thin, manufactured object pushed by the radiation pressure from starlight. Its tumbling motion could be the debris of a larger structure that had broken apart, a discarded piece of an interstellar vessel drifting through the galaxy. The scientific community remains deeply divided. Many astronomers maintain that while Oumuamua is weird, attributing it to aliens is a leap, and that we should exhaust natural explanations first. They argue it could be an exotic type of comet, perhaps one with a surface crust that sealed its gases inside, allowing for outgassing through unseen cracks. The true frustration is that we will never know for sure. Oumuamua is now far beyond the reach of our probes, speeding back into the interstellar dark. It was a messenger that passed through our cosmic neighborhood, leaving behind a single, cryptic clue. Was it a hydrogen iceberg, a fragment of a shattered planet, or a relic from a civilization far away? Its brief visit reminds us that the galaxy is likely filled with objects we have never dreamed of, and that some mysteries simply sail on by forever unanswered. Our galaxy is not drifting through a static void. It is caught in a vast, silent river flowing toward an unseen destination. This is the mystery of the Great Attractor, a colossal gravitational anomaly located in the depths of intergalactic space. It exerts a pull so immense that our entire Milky Way, along with thousands of other galaxies, is being drawn toward it at a staggering speed of over 2 million kilometers per hour. We are all part of a cosmic migration, a flow of galaxies on a scale that is almost impossible to comprehend. The source of this pull, however, lies hidden behind a cosmic curtain. Its heart is positioned in a region of the sky astronomers call the zone of avoidance. This is not a place of danger, but a simple problem of perspective. It is the central plane of our own Milky Way galaxy, a thick band of stars, gas, and dust so dense that it completely obscures our view of the universe beyond. Trying to see the Great Attractor from Earth is like trying to spot a distant mountain range while standing in a deep, foggy valley. For decades, the core of this mystery remained a blur. Then we mapped the currents. Astronomers realized that the Great Attractor is not the final destination, but merely a waypoint in a much larger journey. Our local group of galaxies, including the Milky Way and Andromeda, is part of the Laniakea supercluster. Laniakea is a Hawaiian word meaning immense heaven, and it is a fitting name for a structure that contains over 100,000 galaxies stretching across 500 million light-years. The Great Attractor sits at the heart of Laniakea, a gravitational anchor point around which all these galaxies slowly swirl, but the river does not stop there. Laniakea itself is moving, pulled by an even more massive concentration of matter billions of light-years away, known as the Shapley Attractor. We are caught in a hierarchy of flows, a cosmic watershed where entire superclusters slide along filaments of dark matter toward the densest points in the cosmic web. What could possibly possess enough mass to command such motion? The Great Attractor is likely a supercluster within a supercluster, a node where several immense filaments of the cosmic web intersect, creating a gravitational well of almost unimaginable depth. It is a monument to the power of dark matter, whose unseen scaffolding guides the motion of the visible universe. How does it feel to know that your home, your planet, your very galaxy, is a passenger on this billion-year voyage toward an unseen giant? We are sailing on a hidden tide, and the map to our ultimate destination is still being drawn. Our planet's oldest rocks tell a story of liquid water flowing over 4 billion years ago. This presents a profound contradiction known as the faint young sun paradox. Our sun, like all stars of its type, grows steadily brighter as it ages. Models show that in its youth, the sun was about 30% dimmer than it is today. With that weaker sunlight, Earth should have been a global snowball, a frozen world locked in ice from pole to pole. Yet the geological record is clear. Our young planet was warm and wet, a perfect cradle for the first stirrings of life. How did Earth solve this cosmic heating problem? One of the leading solutions involves a planetary blanket, a much thicker atmosphere rich in potent greenhouse gases like methane and ammonia. These gases are incredibly effective at trapping heat, creating a super-powered greenhouse effect that could have compensated for the faint sun's weak rays. Imagine the early Earth shrouded in a hazy orange sky, its surface kept warm not by the strength of the sun, but by the planet's own insulating jacket. Another compelling idea points to the planet's face itself. With less continental landmass, the young Earth may have been a much darker blue, absorbing more of the sun's precious energy. Or perhaps the atmosphere contained far less of the reflective cloud cover we see today, allowing more sunlight to reach the surface unimpeded. There is even a more exotic possibility that a different kind of greenhouse effect was at work, one driven by a high-pressure atmosphere itself, where the sheer weight of the air created a natural warming effect regardless of its composition. Each of these solutions paints a picture of a world radically different from our own, a planet that employed every trick in the book to remain hospitable. This paradox forces us to reconsider the very definition of a habitable zone. It suggests that a planet's biology and geology are not passive recipients of starlight, but active partners in regulating its climate. Life itself may have played a role, with early microbes releasing methane and helping to thicken the atmospheric blanket that kept them warm. The faint young sun paradox is more than a puzzle about our past. It is a key to finding life elsewhere. If a planet can so ingeniously overcome the limitations of its star, then the galaxy's habitable real estate may be far larger than we ever dreamed. Dark matter is supposed to be the universal glue, the unseen hand present in every galaxy. But what happens when we find a galaxy that seems to be missing its ghost? The discovery of a galaxy called NGC 1052DF2 sent shockwaves through the world of astronomy. This large, diffuse galaxy, roughly the size of our own Milky Way, contains only about 1/400th the number of stars. When scientists measured the motions of its star clusters to weigh it, they found something astonishing. The clusters were moving slowly, exactly as you would expect from the gravitational pull of the visible stars alone. There was no extra mass, no sign of the immense dark matter halo that should be holding the entire structure together. This galaxy appears to be made of normal matter and nothing more. It is a celestial phantom limb, a place where the universe's most abundant material is conspicuously absent. This single observation challenges the very foundation of our cosmic models. If dark matter is a particle that clumps around all galaxies, then how did this one manage to form without it? One compelling theory suggests a violent past. Perhaps NGC 1052DF2 was once a normal galaxy, complete with its dark matter halo, that had a catastrophic encounter with a much larger neighbor. In this cosmic sideswipe, the dark matter, which does not interact with itself or normal matter, could have been stripped away, while the gas and stars, colliding and interacting, were left behind to form this strange, ghost-free object. It would be like a car wreck where the passengers are thrown clear, but the invisible framework of the vehicle is ripped away and lost. Yet this explanation is not without its problems. Other similar galaxies have since been found, and they do not always appear to be near a larger galaxy that could have robbed them. This raises a far more radical question. What if our understanding of gravity itself is wrong? The theory of modified Newtonian dynamics, or MUND, proposes that on the scale of galaxies, gravity behaves differently than Einstein or Newton predicted. It becomes stronger in regions of very low acceleration, eliminating the need for dark matter entirely. In a MUND universe, a galaxy like NGC 1052 DF2 is not an anomaly. It is exactly what the theory predicts. Its slow-moving star clusters are not evidence of missing mass, but proof that gravity works as modified MUND expects in such a diffuse environment, so we are left with a stark choice. Is this galaxy the result of a rare and violent galactic theft, proving dark matter is a real substance that can be taken away? Or is it a crucial piece of evidence that we have been misreading the laws of gravity all along, and the ghost was never there to begin with? The existence of a galaxy without its shadow forces us to look at every assumption and wonder if the universe is playing by a different set of rules than we thought. Deep within the cosmic tapestry, there exists a hole so vast it defies comprehension. This is the Boötes Void, a spherical region of space spanning 330 million light-years where there is almost nothing at all. To grasp its scale, if you placed our Milky Way galaxy at its center, the nearest edge of this emptiness would be over 160 million light-years away in every direction. A sphere of near-total blackness large enough to contain thousands of galaxies typically holds only a few dozen. It is a cosmic desert on a scale that should not exist. How could a region this large, born from a Big Bang that seeded the universe with a relatively even distribution of matter, end up so empty? One theory paints a picture of a giant cosmic bubble. In the early universe, small density fluctuations began to grow, with gravity pulling matter into the denser regions. The Boötes Void could be the flip side of this process, a vast underdensity that was left behind as matter drained away to form the surrounding superclusters. Imagine a block of foam where the bubbles are the voids and the soapy walls are the galaxy filaments. The Boötes Void would be one of the largest bubbles, a cavern carved out by the relentless pull of gravity over billions of years. Yet its sheer emptiness pushes this idea to its limits, leaving some to wonder if a more exotic process is at work. An even more mind-bending possibility is that this void is a scar, a fossilized imprint of a collision with another universe. In the framework of the multiverse, our cosmos could be one bubble in a frothing sea of reality. If our universe bumped against a neighboring one in the distant past, the interaction could have transferred energy and fundamentally altered the distribution of matter in that region, pushing it away and creating a permanent barren patch. This theory suggests the Boötes Void is not an emptiness, but a bruise on our cosmos, evidence of a reality beyond our own. The handful of galaxies that do cling to life within this great nothingness are themselves objects of intense study. What kind of galaxies can form and survive in such profound isolation, cut off from the rich flows of intergalactic gas that fuel star formation in denser regions? They are hermits in an ocean of darkness, their evolution shaped by the void around them. Is this colossal emptiness a natural, if extreme, product of cosmic structure, or is it a window into a multiverse we can never directly see? The Boötes Void is a silent question written across millions of light-years, a reminder that the universe's greatest structures might be the spaces in between. A star located 1,500 light-years away in the constellation Cygnus behaves like nothing else we have ever seen. KIC 8462852, known as Tabby's star, flickers and fades in a pattern so bizarre it defies all standard classification. Most stars show tiny, regular dips in brightness when an orbiting planet passes in front of them. Tabby's star does something completely different. its light will drop by staggering amounts, up to 22%, in chaotic, asymmetrical plunges that can last for days or even weeks. This is not the gentle, repeating shadow of a planet. It is as if something massive, irregular, and unpredictable is repeatedly moving between us and the star, blocking its light in a frantic, unpredictable dance. The initial discovery, made by citizen scientists sifting through data from the Kepler Space Telescope, sent astronomers scrambling for an explanation. The first and most natural idea was a colossal swarm of comets. Perhaps a family of millions of icy bodies, shrouded in thick dust, was orbiting the star in a tight formation, their debris causing the complex pattern of dimming. But this theory began to crack under the weight of further observation. To create the deep dimming we see, the number of comets required would be almost unimaginably vast, far beyond anything in our own solar system. Even more damning was the analysis of infrared light. A giant cloud of cometary dust should glow with waste heat, but Tabby's star showed no such excess infrared signature. The dust was there, but not nearly enough to explain the extreme eclipses. As natural explanations faltered, a more sensational possibility emerged. Could this be evidence of an alien megastructure? The physicist Freeman Dyson once speculated that a sufficiently advanced civilization might eventually build a vast array of energy collectors around its star, a Dyson sphere, to harness its entire power output. What we were seeing, some suggested, could be the partially constructed, lopsided framework of such a project, a tangled web of platforms and panels sporadically blocking the starlight. The idea was intoxicating, a potential beacon of intelligence in the cosmic dark. Yet extraordinary claims require extraordinary evidence, and the star had more secrets to reveal. Long-term studies of its archival data uncovered an even deeper mystery. Over the past century, Tabby's star has been undergoing a long-term secular dimming. Its overall brightness has faded by a significant amount, a trend that no swarm of comets or alien construction project easily explains. This points to something intrinsic to the star itself, or to a vast, cold cloud of fine dust orbiting within the system that we cannot yet directly image. The current leading theory involves this very dust. Perhaps a planet or a family of moons experienced a catastrophic collision, pulverizing themselves into a massive, clumpy ring of debris. This cloud, filled with fragments of all sizes, could now be on a long, eccentric orbit around the star, causing both the short-term, deep dips and the long-term fading as its finer particles slowly disperse. But the mystery is far from solved. The dips remain unpredictable, their patterns too complex and varied to be neatly modeled. Each new observation rules out one possibility while deepening the enigma of what exactly is orbiting this strange star. Is it the aftermath of a planetary disaster, a natural phenomenon we have never witnessed before, or something else entirely? Tabby's star stands as a humbling reminder that the universe is still capable of producing complete surprises, forcing us to look with fresh eyes at the familiar twinkling of the sky and wonder what other strange stories are written in the light. Our universe was forged in a single, searing moment of creation, and the recipe for its first elements should be simple, yet one key ingredient is mysteriously missing. This is the lithium problem, a cosmic accounting error written into the oldest stars in the galaxy. According to our most precise models of the Big Bang, the violent nuclear furnace of the first few minutes should have produced a specific trace amount of a light metal called lithium-7. This prediction is a cornerstone of Big Bang nucleosynthesis, the theory that successfully explains the cosmic abundances of hydrogen and helium. The math is elegant and it works beautifully for the other light elements. But when astronomers point their telescopes at the most ancient stars in the Milky Way, stars that formed from the pristine, uncontaminated material of the early universe, they find only about 1/3 the amount of lithium that our models insist should be there. A vast quantity of this primordial element has simply vanished. Where did it go? One possibility is that our understanding of the Big Bang itself is subtly flawed. Perhaps there is an unknown particle, like a certain type of neutrino, that was present in those first moments and subtly altered the nuclear reactions, suppressing the production of lithium. This would mean that the universe's first recipe needs a revision, a new line in the instructions we have been following for decades. The other leading theory is that the lithium was created as predicted, but something has been systematically destroying it for billions of years. These ancient stars act as cosmic time capsules, and as they slowly burn their hydrogen fuel, their internal churning could be dragging surface lithium down into their hotter, deeper layers, where it is torn apart in nuclear reactions. It is like a slow-motion conveyor belt carrying ice into a furnace. The problem is that our best models of stellar physics cannot make this process efficient enough to account for all the missing lithium. The destruction is not fast or thorough enough to explain the dramatic shortfall we observe. Could there be another, more exotic mechanism at work? What if certain cosmic events, like the explosive deaths of the very first stars, created powerful waves that swept through the early galaxy, selectively spalling lithium off the surfaces of other stars? Or perhaps the lithium is hiding in plain sight, bound up in molecules within cold clouds of interstellar dust, invisible to our current methods of detection. The lithium problem is a quiet but persistent thorn in the side of cosmology. It tells us that even our most successful and celebrated theories might be missing a crucial piece of the puzzle, a single, overlooked detail from the universe's first 3 minutes that echoes through billions of years. Floating within the faint afterglow of creation is a cosmic bruise, a cold spot so vast and profound it challenges our understanding of reality itself. This feature in the cosmic microwave background is not just a minor temperature fluctuation, it is an anomaly on a grand scale, a region hundreds of times larger than a typical variation and significantly colder than its surroundings. When scientists first confirmed its existence, it stood out as a statistical ghost, something that should be incredibly rare, perhaps even impossible, within our standard model of the cosmos. The question became immediate and unsettling. What could have left such a colossal mark on the infant universe? One compelling explanation lies in the architecture of nothingness. This is the supervoid hypothesis, which suggests the cold spot is not a feature of the primordial universe at all, but a secondary effect. According to this idea, between us and the cosmic microwave background lies a truly enormous void, a region of space spanning billions of light years that is almost completely empty of galaxies and dark matter. When light from the Big Bang's afterglow travels through such a void, it must climb out of this immense gravitational well. The photons lose energy on this cosmic uphill journey, stretching to longer, redder wavelengths which we perceive as a drop in temperature. It is a phenomenon known as the integrated Sachs-Wolf effect, a subtle but real cooling caused by the expansion of the universe tugging at light as it traverses vast emptiness. The hunt was on to find this proposed supervoid. Astronomers have indeed identified a large underdense region in the direction of the cold spot, but there is a critical problem of scale. The void we have found, while enormous, is not nearly large or empty enough to account for the profound cooling we observe. The numbers simply do not add up, leaving the supervoid explanation as a possible contributor, but not the sole culprit for such an extreme anomaly. This failure of a natural explanation opens the door to a truly breathtaking possibility, one that reaches beyond our single universe. Some theoretical physicists propose that the cold spot is a collision scar, a fossilized imprint from a time when our universe violently bumped into another, separate bubble of reality in the multiverse. In the chaotic froth of eternal inflation, where countless universes are constantly bubbling into existence, such collisions, while rare, are possible. The energy released in such a cosmic fender bender would have been unimaginable, and it could have locally drained energy from the plasma of our young cosmos, leaving behind a permanent cold patch on the sky, a cosmic kiss from a universe we can never otherwise perceive. This idea remains highly speculative, a ghost in the equations of cosmology, yet its mere consideration forces us to confront the limits of our knowledge. Is this cold spot simply the most extreme statistical fluke in a vast and random cosmos, a one-in-a-million roll of the dice that just happened to land in our field of view? Or is it the first tangible evidence, a cosmic fingerprint, suggesting that our universe is not alone, but is one of countless others in an immeasurably vast multiverse? The answer is written in the cold, a whisper from the dawn of time that we are only just beginning to hear. Even the vacuum of space is not as empty as it seems. For an astronaut floating at a constant velocity, the cosmos is a cold, silent void, a perfect emptiness. But if that same astronaut were to fire their engines and accelerate, something truly bizarre would happen. Their entire reality would shift. They would suddenly find themselves bathed in a warm glow of particles, a gentle heat where there was only cold nothingness before. This is the Unravel effect, a strange prediction from the marriage of quantum field theory and Einstein's special relativity. It tells us that the concept of a particle is not absolute, but depends entirely on your state of motion. What one observer measures as an empty vacuum, another, accelerating observer, measures as a busy soup of real particles. The energy for this phantom radiation comes directly from the acceleration itself. The faster you accelerate, the hotter this ghostly bath of particles becomes. Picture an observer undergoing extreme acceleration, perhaps falling toward a black hole. For them, the void would be blazing with Unravel radiation, a thermal blanket of their own making. This is not just a mathematical curiosity. It has a profound and direct connection to one of the most famous phenomena in physics, Hawking radiation. The event horizon of a black hole creates a situation where the acceleration needed to stay stationary, to avoid falling in, becomes infinite. This ultimate acceleration is what makes the black hole appear to radiate. The Unravel effect provides a crucial window into understanding how Hawking radiation can emerge from the quantum froth at the edge of a black hole. It suggests that gravity itself may not be a fundamental force, but rather a thermodynamic phenomenon, an emergent consequence of quantum information and entropy, much like how the temperature of a gas emerges from the random motion of countless molecules. The Unravel effect blurs the line between motion and heat, between inertia and temperature, forcing us to ask a deeply unsettling question. Is our perception of an empty, objective universe just an illusion, a comforting story we tell ourselves because we are not accelerating fast enough to see the seething, energetic truth hidden within the void? The very heart of our galaxy is screaming in a voice we are only just learning to hear. This scream is not made of sound, but of light, the most powerful light in the universe. From the crowded core of the Milky Way, an intense and unexplained excess of gamma-ray radiation floods into our telescopes. This galactic center excess is a brilliant mystery, a beacon of pure energy that should not exist in such abundance. It is as if we have discovered a cosmic engine hidden behind clouds of dust and stars, running at full power for reasons we cannot yet fathom. For scientists, this gamma-ray glow presents a tantalizing puzzle with two deeply compelling yet opposing solutions. One possibility touches the very nature of the universe's greatest ghost. The center of the galaxy is thought to be the densest region of dark matter in our vicinity. If dark matter is made of WIMP, those hypothetical weakly interacting massive particles, then they might not be completely stable. When two of these particles collide, the theory goes, they could annihilate each other in a flash of energy, producing the very gamma rays we observe. This would be the ultimate signature, the first indirect proof of dark matter's particle nature, a discovery that would rewrite physics. the galactic center would be a colossal dark matter demolition site, its silent, invisible particles constantly destroying each other and lighting up the sky with their final brilliant burst. Yet there is another, more mundane explanation that is equally fascinating. The galactic center is a stellar metropolis packed with the corpses of dead stars. Among these are pulsars, the rapidly spinning, city-sized cores of exploded stars that beam radiation like a lighthouse. Thousands of these faint, old pulsars could be gathered in the galactic core, each one too dim for us to see individually from our distant vantage point. But collectively, their combined gamma-ray hum could perfectly mimic the smooth, diffuse glow we attribute to dark matter annihilation. It would be like standing in a city and hearing the roar of a distant crowd. You cannot pick out any single voice, but the collective sound is unmistakable. Distinguishing between these two possibilities is one of the most difficult challenges in modern astrophysics. How do you tell the difference between the death cry of the universe's most elusive substance and the combined whisper of countless stellar ghosts? The answer lies in the fine details of the light itself. If the glow comes from dark matter, it should be perfectly smooth and symmetric, a featureless cloud emanating from the spherical dark matter halo. If it comes from pulsars, the signal should be slightly clumpy, made up of many individual point-like sources that we simply cannot resolve with our current instruments. Our telescopes are caught in a cosmic balancing act, straining to see if this brilliant excess is the smooth signature of a fundamental discovery or the grainy texture of a stellar graveyard. The answer will not come easily, but its implications are profound. Is the heart of our galaxy illuminated by the death of dark matter, or is it simply shining with the quiet, collective light of its dead? The truth is written in gamma rays, a secret we are desperately trying to decode. High above the cloud tops of Saturn, a perfect geometric storm rages. Encircling the gas giant's north pole is a colossal hexagon, a six-sided jet stream so vast that the entire Earth could fit neatly inside its swirling walls. This is not a fleeting cloud formation, but a permanent atmospheric feature, a precise polygon etched into the planet's sky for decades and likely much longer. How can a fluid, chaotic atmosphere like Saturn's produce and maintain such a rigid, geometric shape? The answer lies in a delicate dance between rotation and shear. Imagine stirring a cup of tea very quickly. As the fluid spins, you might see smaller, temporary swirls and patterns emerge. On a planetary scale, Saturn's rapid rotation acts as that stirring spoon, creating powerful eastward jet streams. The hexagon appears to be a standing wave pattern pinned to the planet's north pole, a stable, self-reinforcing oscillation within this flowing atmospheric river. It is like a cosmic harmonic, a note played on the strings of the atmosphere that simply will not fade. Laboratory experiments here on Earth have recreated similar, though much smaller and shorter-lived, polygonal shapes in spinning fluids. When a fluid rotates at one speed and a central core rotates at a different rate, the shear between these layers can generate instabilities that snap into geometric forms. On Saturn, the deep, churning heat from the planet's interior likely provides the energy, while the planet's own rapid spin provides the structure, locking this atmospheric wave into a stable, six-sided form. But why six sides? The number of sides in such a pattern is thought to depend on the specific speed and depth of the jet stream. The physics suggests that under Saturn's unique conditions, a hexagonal shape is the most stable and efficient configuration, the path of least resistance for the planet's furious atmospheric energy. This makes the hexagon a natural, if stunningly rare, weather phenomenon. Yet its longevity is what truly baffles scientists. Storms on Earth, even the largest hurricanes, are powered by the sun's heat and dissipate in a matter of days. Saturn's hexagon, however, has persisted through multiple seasons, enduring decades of sunlight and polar darkness without losing its iconic shape. It is a self-sustaining engine, a perpetual motion machine sculpted from wind and gas. What does this teach us about the hidden workings of giant planets? The Saturn hexagon is a laboratory for extreme fluid dynamics, a natural experiment on a scale we could never hope to build. By studying its stability, we gain clues about the currents that flow thousands of miles beneath the visible cloud tops, and about the fundamental ways rotating fluids behave across the cosmos. This perfect shape, a jewel in Saturn's crown, is more than a beautiful curiosity. It is a testament to the universe's hidden order, a reminder that even in the chaos of a storm, the laws of physics can write their signature in geometry. Some of the universe's most brilliant stars are living on borrowed time. Luminous blue variables are the rock stars of the cosmos, colossal hypergiants so massive and unstable that their very brilliance threatens to tear them apart. They are not calm, steady furnaces like our sun. These are stellar behemoths in their final, desperate acts, prone to violent, unpredictable eruptions that defy our understanding of how stars behave. During these outbursts, a single star can eject an amount of material equal to the mass of our entire sun, casting off a vast shell of gas that glows like a cosmic smoke ring. This is stellar evolution in its most extreme and dramatic form. The fundamental mystery surrounding these giants is what their final fate will be. Their immense size places them on a razor's edge between two spectacularly different endings. One path leads to a pair instability supernova, a detonation of almost unimaginable power. In the core of such a massive star, the energy of light itself can spontaneously create pairs of electrons and positrons. This process robs the core of the outward radiation pressure that was supporting it against its own immense gravity. The star's core collapses in an instant, triggering a runaway thermonuclear explosion that is so complete it leaves no remnant behind. The entire star is utterly obliterated, scattering its enriched guts across the galaxy in a flash of light that can outshine an entire galaxy. But there is another, even more silent and terrifying possibility. What if the star is so supremely massive that not even a pair instability supernova can occur? What if its gravity is simply too strong? In this scenario, the core's collapse may be unstoppable. There would be no titanic explosion, no brilliant flash to mark its passing. The star would simply wink out of existence, its entire mass collapsing directly into a black hole without a supernova. It would be the ultimate cosmic ghosting, a stellar giant vanishing from the sky, leaving only a gravitational tombstone behind. So, which is it? Are these luminous, erupting variables the final warning cries before a universe-shattering supernova? Or are they the last flickers of a star destined to be swallowed by its own shadow? We watch these brilliant, unstable giants with a sense of awe and trepidation, knowing that their final performance will reveal one of the universe's most profound secrets about the death of the largest stars ever born. Particles from the depths of space strike our atmosphere with energies that defy belief. These are cosmic rays, atomic nuclei traveling at nearly the speed of light, and the most powerful among them carry a punch that seems to break the rules of physics. One such particle, detected in 1991, was so impossibly energetic it was nicknamed the "Oh my God" particle. It was a single proton, a subatomic speck, moving with the kinetic energy of a well-thrown baseball. Think about that for a moment, a single elementary particle, billions of times smaller than a grain of sand, packed with the energy of a macroscopic object in motion. According to our best theories, such a particle should not be able to travel very far through the cosmos. The universe is filled with the faint glow of the cosmic microwave background radiation, a relic from the Big Bang. For a proton moving this fast, that radiation is no longer a gentle whisper. It becomes a wall of high-energy gamma rays. The "Oh my God" particle should have slammed into this photon barrier and bled away its energy long before it ever reached Earth. Its very existence is a paradox, a cosmic speeding ticket for a particle that should not be able to go that fast. The mystery deepens when we try to find their source. These ultra-high energy cosmic rays are electrically charged, which means their paths are twisted and bent by the galaxy's invisible magnetic fields as they travel. It is like trying to trace the path of a pinball by where it finally lands. By the time one of these particles hits our atmosphere, creating a shower of secondary particles, its original trajectory has been completely scrambled. We know a cosmic bullet hit us, but we have no clear line back to the shooter. What cosmic particle accelerator is powerful enough to create such monstrosities? The usual suspects, like the supermassive black holes at the centers of active galaxies, are candidates, but even their immense power is stretched to the limit to explain the "oh my god" particle. Some theories point to the cataclysmic collisions of entire galaxies, or perhaps the violent deaths of hypergiant stars we have not yet classified. There is even the speculative possibility that these rays are the signature of exotic and decayed relics from the very early universe, like cosmic strings or magnetic monopoles, objects predicted by theory but never seen. Every time one of these ultra-high energy particles streaks through our detectors, it is a message from the most violent and energetic processes in the universe. Yet the message is written in a code we cannot fully decipher, its origin obscured and its energy a profound challenge to our understanding of nature's limits. What unimaginable forces are hurling these atomic fragments across the cosmos, and what will their secrets teach us about the extreme edges of physics? From the ghostly pull of dark matter to the silent, screaming heart of our galaxy, these 25 cosmic mysteries define the very frontier of our understanding. They are not dead ends, but vibrant, open doors, each one, from the faint young sun paradox to the impossible energy of the "oh my god" particle, is a testament to a universe that refuses to be fully known, a constant invitation to look deeper and question further. Every unanswered question is a new beginning for discovery, a puzzle waiting for its solver. The cosmic horizon is not a limit, but a promise of endless wonder. So we turn the question to you. Which of these enigmas captures your imagination the most? Is it the profound silence of the Fermi Paradox, the bizarre geometry of Saturn's hexagon, or the haunting possibility of a multiverse written in a cold spot on the sky? Share your thoughts and never stop looking up at the stars with a sense of awe. For in the great unknown, the next great discovery is always waiting just beyond the edge of sight.